developing in my group. Oops. Yep. So let me start. Okay, so the vision of having personal robotic assistants, this general purpose robotics that we are discussing right now, it's a long-wished vision among the AI and robotics researchers. Even from the beginning, when the early robots entered the industry in the late 60s, we have envisioned having such robots in our houses, preparing our breakfast. And I mean, there are many things that can go wrong. But yet, it's been now 50, 60 years, and we know that we are not there yet, but still we are depicting our robots having like human-like characteristics, being able to perceive the objects and the humans around them. They can learn to perform household assistive tasks, and they can adapt to humans and their needs. But why don't we have such robots yet? Well, I would argue that in the past we didn't have the hardware and the algorithms, but now things are changing. Now we have robots with anthropomorphic bodies and increased dexterity. We have computational power thanks to the faster CPUs and the clusters of GPUs. We have cheaper, fast, and more accurate sensors, and thanks to the deep learning revolution, we have better algorithms for perception. So what are we still missing? I believe that we are missing several components still, and now it's the time that we have to address these challenges in order for our robots to break the walls of the lab setting and be able to enter into human-inhabited environments. And among these problems, what I am focusing on in my research is learning manipulation skills in a sample efficient way, doing assistive task planning and learning interactions with the environment and with humans. And so how do we achieve this? How do we bring the robots then in our homes, for example? I identify three particular problems in my research, and I will focus on some of them during this talk, but I would like to summarize. So first of all, hesitant human-robot interactions. Usually what happens is that the human adapts to the robot and not the other way around. Then we have restricted and non-generalizable manipulation skills. While we have done amazing progress by bringing learning into robotics on solving tabletop tasks and beam picking, we are still challenged in more complicated tasks like mobile manipulation. And finally, we have non-adaptive robot behavior, in particular when behaviors that scale into long horizons. So what do we do about this? My idea is that we have to introduce, of course, the learning mechanisms into robotics such that we can overcome the limitations. And my vision is that we can leverage the generalization power of machine learning, but together with classical robotic approaches, such that we can make them scale into the real world. Because we have to remember that we are building on top of the shoulders of giants, and there was a lot of work before us. So I will go through my path, I would say, to scaling robot learning, and I will focus on our works that we did on incorporating models and learning better models for model-based reinforcement learning, how we can learn and incorporate priors in optimization methods, and finally, how we can integrate structure and learn from structured data. So let me start from the first part with the model predictive actor critic algorithm. So we started as everyone with deep reinforcement learning. We were super excited about the different algorithms that were able to solve many different challenging tasks. However, we know that they are sample inefficient. Most of the tasks require hundreds of thousands, millions of interactions. And this is not something that you would like to do with your real robot. So leveraging the inspiration from works like the model-based policy optimization, where they learn a model through this data that you collect by interacting with the environment, what they did is that they randomly sample some actions from the model and then use this data in order to speed up the learning of soft actor critic algorithm, for example. On the other hand, what we thought about is that, okay, well, we have the data, we can do maximum entropy exploration in order to visit these states, for example, that we haven't modeled into our dynamics. Then we can also approximate good value functions through our actor critic algorithm, and this would allow us to actually do better planning. And what we actually do is that we train a model through these interactions with the environment, and instead of greedily taking actions with this learned model, we actually do planning in this latent MDP. And by doing planning in this approximated MDP of the real environment, we are able to collect, do you want me to stop? Okay, so by this model-based planning, we can collect locally good samples through incorporating approaches like kind of model predictive path integrals. So in this way, we can even raise the margin of the acceleration. And this is, for example, our results with blue. You see the performance of MOPA compared to the other approaches in the standard simulator control tasks of the workers of the OpenAI gene. And as I said, what we want in reality is to see if we can use these algorithms on real robots. And indeed, we used these algorithms for training from scratch a robotic hand. This is a four-finger hand from the Yale University, from the Grab Lab. And what the task here is to grasp the valve and rotate it till we actually open the valve. So it has to reach a desired orientation. And you can see that we can train with MOPAC pretty fast, much faster than the other methods. And of course, we have to attribute some of these performance also to the compliance of this robotic hand. Next, we wanted to challenge even more our algorithm, and we executed a finger gating task. In this case, the depicted apple has to be grasped, and then you have to finger gate. This means you have to rotate, regrasp, rotate, regrasp, till you reach the desired orientation, the desired pose, without dropping the apple, and also without orienting it in different axes. That is not your goal. And again, we had a higher margin, and we are still working on it. So we are trying basically to integrate visual features into this training process, because right now we are relying on capturing with April tags. We are using April tags to actually detect the pose of the object. But learning better dynamics model for model-based reinforcement learning is actually a very challenging task, and many people have approached it through different ways. So in order to address this challenge in recent work, we tried to integrate some intrinsic exploration into model predictive control, such that while we are planning, we are trying also to visit these unmodeled transitions into our dynamics. In particular, this is challenging when a robot executes tasks that require continuous contact with the environment, but also you are getting sparse rewards. So you only get a reward if you reach the end goal of the task. So in our approach, we proposed model-based active exploration, and what we did is that we included into the objective of model predictive control that usually you care about the cumulative reward during your rollout. We integrated an information gain objective using an ensemble of probabilistic model predictive controllers that would incentivize through a mutual information actually objective to visit the state action pairs that would potentially increase your expected returns. And this we used initially in simulation in order to see how the agent can learn to reach goals. This is a tilted table, and the robot doesn't know the goal. It has to discover the goal. They are not goal specific, these policies. It has to learn to balance the ball while trying to explore the environment such that it finds the goal. And on the right side, you see the exploration of the environment, how progressively while planning, it explores also the environment in order to learn the dynamics and finally find the goal position. And we use the same methodology to train from scratch our real robot with different tilted environments. And we found out that initially the agent was trying basically to learn how to balance the ball. And once it actually decoded these dynamics, it was able to explore and find the goal locations in real time. So it was spinning the ball and reaching the goal. Now, there are though tasks from which demonstrations, for example, could be very, very useful. And I think some of our speakers before have touched already onto this problem of learning rewards or learning cost functions in our case. In particular, when you have multi-objective tasks and you don't want to learn only this particular skill, for example, that just pushes a ball to a goal, you need to care about multiple objectives into your problem, then you may be able to figure out some of your cost functions from demonstrations. So in a recent work, we proposed to learn implicit priors for motion optimization. In this case, we use as an implicit model the energy-based models, which can capture multimodalities in the data. They are composable, so they belong to the exponential family. Therefore, they can be composed together with other functions that can be, for example, learned or handcrafted by you. For example, joint limits, it's something that we know already, we don't need to learn it for a specific robot. And they can be represented in arbitrary latent spaces. You don't have to necessarily try to put them on the configuration space, but you can actually learn them on the task space. Now, in order to learn this kind of energy-based models, we need expert trajectories, which we generated using motion planners and which we conditioned on different environments with obstacles. And this is an example that you see of a learned energy landscape that can be used as a prior cost for doing obstacle avoidance with different configurations of obstacles. And what I want to note is that in the way that we trained by incorporating actually the expert trajectories by costly motion planners is that basically you implicitly encode also the dynamics of the, let's say, costly motion planning process. And in the end, you can use these costs that you learned that are in the end probabilistic models as inside the planning as inference framework, compose them together with other costs because you are training with log likelihood and then everything ends up being an energy of state and actions. And you can use, for example, stochastic Gaussian process motion planning in order to plan through these environments. And you can see here for different types of goals, how you can reach goal positions. So this is like multiple goals sampled from a single initial configuration. And you can also integrate it with other tasks like pouring that it is very difficult to specify. And in this particular case, we show in the paper how you can actually learn phase conditioned trajectories because actually it matters the exact timing in which you are going to pour. I am not visualizing here the energy because it's high dimensional, it's in 6D. And we have transferred this into the real robot without needing any retraining. We conditioned it, we also coupled it with obstacle avoidance, joint limits, and also smoothness in the trajectory. And we were able, for example, to change the scene, rearrange the obstacles, and still be able to pour these balls into the ball for different orientations. And actually, one thing that I didn't include here, but I want to note is that also in terms of finding the optimal plan, this approach was better computationally. Now, in a follow-up work, we were interested to also resolve the problem of grasping. And we found out that if we train energy-based models by denoising score matching, so in another sense, doing learning by diffusion, you are able to actually learn the probabilistic model of the grasp on the object manifold. And in this particular case, you are able to produce gradient field over all the possible grasps on the manifold of the object. And this allows you, this is an example of the diffusion that you can actually use with stochastic gradient Lagrangian dynamics directly in order to do a joint grasp and motion optimization based on gradient-based optimization, in which you resolve in a single optimization loop both the actual grasping pose and multiple, in this case, it's like a compilation of multiple grasping poses in the end. And we showed that actually this yields a better result than decoupling. Okay, first I will sample a bunch of grasps, and then I will see for each grasp if there is a follow-up motion plan that can reach a target location. And we have also transferred this in picking with occlusion, pick and placing, restrained environments like with shelves, and also picking and reorienting in some abstract 6D poses, and all of them in a single optimization loop. And finally, we have also transferred this into the real robot. A caveat here is that you have to know the pose of the object. So in these examples here, we used OptiTrack in order to detect the pose of the object. We can consider that we have a very nice pose detector that works pretty well. We also tried with directly with point clouds. This led to some drop into the performance, but we are still working on it. So I think there are also other ways that we can integrate to make it work also directly from point clouds, if we want, of course. But yeah, the important thing here is that these can also be an energy and cost function that you can couple with other kind of cost functions that you learned, that you, for example, hand designed, because it's trivial to design some things like the smoothness in the trajectory and execute directly trajectory optimization through all these objectives. Now, in the follow-up work, I will discuss the idea of combining both priors and structure. Now, I would argue that even the previous work incorporates structure, because basically you are structuring your problem with these specific cost functions. But here in this follow-up work, we explicitly encoded the geometry of the scene into a reinforcement learning agent. Now, I will give you some context to understand why we are doing this work. What you see here is some abstract designs that an architect may give you. So this is from a project that we do with the architectural department at TU Darmstadt, where the architects envision that they are going to give us a 3D shape or like abstract shapes, and they will give us some blocks, and then we will find out the best way in order to fulfill this design. So we don't have a priori the goal positions of the objects, or they don't even know if what they ask for us is feasible by the robot. So it is a combinatorial optimization problem. You need to derive all the sequential pick and placing. You need to ensure that this structure will be actually feasible by the robot. You want to ensure that it's going to be stable. So how do you do this? I mean, you could construct several constraints and design it in order to do motion optimization, but then you will have to do this every time they give you a new design, which is not possible, right? So you need an agent that can resolve this relation. So it's both a task planning problem and a geometrical problem. And we found out that graph neural networks are actually very effective into encoding these special relations into the objects compared to the goal state that you want to fulfill. And we could train this with a DQN based approach in order to find the optimal action that you should execute, subject to getting rewards for not colliding with your structure and keeping everything feasible. But doing graph neural networks with reinforcement learning is a very difficult task, and it's a hard exploration problem. So in our follow-up work, we considered the following assumption. What if we have on a high level during the training process a mixed integer linear program, a model-based planner in the end, that can resolve this task of, okay, I have this set of objects, I have this desired volume that I need to fulfill, without taking into account a relaxed problem without taking into account stabilities, collisions, and everything that you would normally take into account if you want to train this, just fulfilling the shape, give us a possible set of solutions. Now, if we take this possible set of solutions as a prior for our graph neural network reinforcement learning agent, we can actually guide the object selection. And moreover, the graph neural network that is overlooking this process of fulfilling the assembly can also, on the low level, if you integrate a grasp and motion planning sequence, that actually, if you have resolved already that, okay, this is the object that you have to take, this is the goal position that you have to achieve, you can basically do motion planning and resolve this problem. But what the GNN can actually learn from this interaction of the low-level planner is which actions are feasible or not, which actions are leading to collisions with the already placed objects, and so on. So in the end, it learns to perform the assembly very successfully. Here you see an example of the heuristic where we take the MILP solution, we create several rules, and we try to execute it with the robot. And you can see that the actually resolution of the collision is a bit challenging, while the reinforcement learning agent, if you also integrate some Monte Carlo tree search in an AlphaGo fashion, outperforms every approach, even our previous end-to-end, let's say, GNNRL approach. And we transferred this method directly to the real robot. It doesn't need retraining because it is a high-level abstraction to this task. And actually, the robot not only executes the task, but also has a stopping action. So it can know where to stop such that it doesn't overbuild and go outside the limits of the abstract design that you want to fulfill. And now I will go to the last part that refers to mobile manipulation. Now, I want to say a few things about why I think like mobile manipulation, and I think we already have seen this with some previous work. It's one of the most promising robotic systems such that we can actually go out there into the world, because they can have a floating base. All the world is their workspace. They can have embodied cameras, embodied perception, so they can operate into the real world. And I would argue that they could solve like 90% of the household tasks that we need. However, one problem is that usually in reinforcement, in mobile manipulation, you need to take both continuous and discrete decisions. For example, in this problem, we only considered as possible actions what is the optimal base post placement, such that we can ensure that objects on tables or different areas are reachable by the robot. And the other action that we have to take into account is whether or not the robot should activate the arm in order to plan a grasp. So if you are very far away, for example, from your most reachable configuration, you don't want to actually start activating or start solving inverse kinematics for no reason, for example. To this end, I will not do many details on how we did it. We integrated we conditioned our continuous policy to the discrete actions, because basically they have to be conditioned on whether or not you are in proximity to the goal or not. And we used a Gamble softmax reparameterization of categorical distributions in order to realize this. But yet there is another issue. The robots, according to their design from hardware side, they have different reachabilities. And there has been a lot of work in mobile manipulation about understanding what is the kinematically reachable poses of mobile manipulators. So what we have here is the operational workspace of the Tiago robot, only for the one arm, which can actually be mapped also on the other arm. And what it has been proposed like about 10 years ago by Warenkamp, Asfour, and Dillman was to consider the floating base paradigm, so that the robot can reach 6D goal poses from any point in the space, do the inverse mapping of this operational workspace such that you can create goals with respect to the abstract locations of the floating base, and use this in order to find possibly good locations from which the robot can reach abstract 60 poses. Now, how does this look like for an arbitrary 60 pose? Consider that we also have to discretize and voxelize the 60 poses, and then you have to take some scores about whether or not these poses can be reachable or not. And this is how it looks like. But then what we thought about is that, okay, and another thing, this is always in the locality of the robot. You cannot reason about, more long horizon tasks. What we thought about was, okay, what if we take this data set that we can collect without acting on any environment, just sampling and taking the workspace of the robot, and create an offline learning approach where you can just create a prior behavior for your mobile manipulator robot. And here is what you actually get by doing a continuous function approximation of all the data sets. And you can see that basically the agent discovers many more possibilities, because in the first approach, in the common approach, you just do certain inverse kinematics, whether you find a solution or not, and this is the end. While the Q function has learned these are good poses in which there is very high probability of fulfilling your end task. Now, what we want to do is use this information, that it is a local information, and integrate it into a learning algorithm that can learn mobile manipulation tasks with increasing complexity. So in order to do this, we introduced a new algorithm called boosted hybrid reinforcement learning that can allow us to transfer knowledge from behavior priors. And how do we achieve this? We achieve it by introducing the concept of boosting. Boosting has been studied in the concept of supervised learning, but it also has been studied in reinforcement learning recently, and is the idea of decomposing challenging tasks into residual tasks. Only that here the residuals are in the Q function, or what it represents about the particular task that you are learning. And in this case, at every time, initially, for example, you train this reachability Q function, that it is your first residual, and then let's say that you want to reach from a very far distance this goal pose, so you want to bias the navigation to go towards its best goal position. So what you need to do is actually only train the residual that comes on top of this task. And then let's say that we have obstacle avoidance. Then again, you can add an additional residual and not caring about retraining, again, a full function approximator or a very complex task. Additionally, I want to say that adding a KL regularization between the previous policy that you had and the new policy is actually very helpful, because it gives you that these intrinsic bonuses that incentivizes that, okay, you are doing a good job, keep this behavior from your previous policy. And we have compared our method with different approaches for learning mobile manipulation, and also for incorporating priors into and doing transferring in reinforcement learning. And you can see the impressive improvement that we have with the blue line, that it is the boosted hybrid RL. And the different tasks that we considered was, as I told you initially, the locality, that was offline training, then adding more space so the robot has to navigate. I'm finishing, yeah, sorry. Then we added obstacles. We added additional objects in the scene that can also play the role of obstacles, and so on. And just a few minutes. We transferred this directly to the real robot without needing any retraining. We were able to do pick and places with different objects in the scene, and we were also able to do object rearrangement, so to transfer the same exact behavior between sequential pick and placing, because in the end, what you care about is the reachability of the robot. So I would have to say, just before I close, that this is not only the things that we need, we still need perception. We need to, for example, be able to learn from human videos by, for example, extracting representations like key points, extract plans, leveraging common sense. We have to take care about the safety. That is something that we didn't have there so much right now. And finally, we need to take into account the embodied perception of our robot and induce the coordination for mobile manipulation. So I would like to thank my collaborators and my students, and yeah, thank you for your attention.